Yeah, I'm John Ludden. I'm the Executive Director of the British Geological Survey, and I'm here today to talk to the GIFT workshop about a subject that I've called lighting up the underworld, which is really about how we want to, or we need to monitor the subsurface to be able to sustainably exploit the resources of the Earth. And I've called this talk Lighting Up the Underworld, which I think is quite a nice title. And it really is sort of all about how we do need to understand what's beneath our feet. And as sort of the British Geological Survey is one of many geological surveys, but we're one of the more research-intensive geological surveys. We actually sit inside the Research Council as opposed to inside a ministry, as many surveys do. And we've recently been funded to the tune of sort of about 40 million euros to actually install some underground laboratories or some underground systems in which we will try and understand how the subsurface behaves during processes such as shale fracking, but also carbon capture, also mineral extraction and such like. And the real message, if you want the strapline or the mission statement that the BGS has, the Geological Survey has, is to understand the subsurface on the scale of a lifetime. So on the scale of your life, we will be able to understand what's going on below your feet. And that's kind of a useful way of expressing it, because in general, geological processes are very slow. As you know, I mean, it takes billions of years for things to happen, or millions of years. So it's hard to sort of communicate the scales to students in the same way as you might communicate the scales on climate change and geographical things. So just before I start, you're a mixture of people who study everything from sort of environmental change to geology. Is that right, or are you mainly? Yeah, okay, so it's quite a mixture of people here. Are there any real geologists in the room? Oh, there are a few. Okay, good. Okay, right, good. So, I'm going to just start with a few words on climate change. You'll have seen this. This is essentially the emission scenario with increasing amount of carbon dioxide emitted, and within this, scientists identified, I'm sure you'll have seen this before, what they call the stabilisation triangles. That's the sort of things you need to do to try and mitigate this increase in carbon dioxide on the planet. And this is the same graph expanded here. So these are the stabilisation triangles. And this was published some time ago, but sort of in a general sense, there are 8 or 9 wedges there, and one wedge avoids 1 billion tons of carbon emissions per year by about 2055. That's that's a kind of nice, simple way of thinking about carbon emissions and what one might need to do to try and sort of solve the problem. And what I'm going to show you is that a lot of the problems that we need to deal with are actually geological problems. And so there's quite an important role for geologists in dealing with these things. And this slide here, sort of as I said, several of these wedges are actually in the remit of a geoscientist or a geologist or an earth scientist. And for example, and here you can see a few of them, a switch from renewable electricity and fuels. Well, that's not necessarily geological, but things like carbon capture and storage are. Things such as nuclear repositories are, and such like. So I'll come back to that in a minute. But there are various ways of dealing with this problem. And so, essentially, this slide used to say, actually, we in the UK have a problem. But I gave this talk recently at a thing called the Deep Carbon Observatory too. So I kind of put we have a problem, because I think it's not. It varies from country to country, but in general, globally we have a problem. And in some cases, in particular countries, they have a more severe problem because their energy mix is such that they have to use hydrocarbons, at least for the moment. Because a relatively populated country such as the UK, 65 million people, you can't get away sort of overnight with a switch from non-hydrocarbons to hydrocarbons. So we know that there's going to be a transition, and the question is how can we achieve this transition? So at least four of the what we call low carbon solutions or lower carbon solutions, some of you might argue that they're not low carbon solutions, but they are lower, are geological. But the big thing is that the public, and you, I think, and your students actually, and in particular your students, need to really develop the confidence, or you need to sort of hopefully portray the confidence to them that we are able to deal with these problems, even though they're quite difficult problems. So that's a bit fuzzy, but those people there, those fuzzy people there are European leaders that you may recognize. And this was I think at the end of last year, and in Europe, I'm not sure whether you're aware of this. In general, energy policy is devolved to the nations, and there isn't a sort of European-wide energy policy, and that's been sort of accepted and underlined recently in saying that EU leaders will adopt a flexible energy and climate targets. That means that they will allow the different nations in Europe to meet the targets in different ways. So there's a target that's been set, right, which is to reduce emissions by 2025, 2050, whatever it is. And that'll actually be underlined, those targets will be underlined again at the Paris meeting in December. But you can meet them by any means you want, right? Better, more efficiency, better insulation, carbon capture and storage, shale gas and such like, and we'll come back to that. So that's quite a change, actually. It means that Europe is not sort of imposing its policy on different nations, because it's actually very hard to do that in Europe. And because this is the sort of theme of this talk here is about minerals as well, I've added a couple of slides on minerals which normally don't fit in this talk, so I apologize, but they do fit with the message. And there are a number of exploration and development projects for metallic minerals currently in the UK. So the UK is a small country, as you know, but it actually has minerals. And the Bronze Age was actually driven by tin that came from the UK and was shipped from Cornwall all the way around into Crete, and that's what drove the Bronze Age. Interestingly, if you see the last slide here, you don't need to read all of this, but it just gives you some idea of the last line, some idea of the activity around the UK, mainly gold and silver, but tin, tungsten, which is in Cornwall, so the famous Cornish granites. I'll show you a little picture in a minute of those, and similarly the Brittany granites, same sort of thing, tin tungsten provinces. Hemerdon, which is a US company owned by Hemerdon, which is an area in Devon owned by, now will be exploited by Wolf Minerals, a US company, and this will be probably in the top 3 tungsten mines on the planet within 5 years. So there is active exploration going on in the UK and active mining. It'll be a very large tungsten open pit mine. The reason for that is because tungsten is one of these strategic metals that we need, that I think people will talk to you about or have talked to you about as time goes on. I keep pushing the wrong thing, sorry. So to sort of add to that and to sort of put that into context, which is the energy context and the subsurface context, you actually, to be able to develop a mine nowadays in a highly populated country like the UK or anywhere in Europe, to be honest, you need to have very, very strong and powerful environmental baselines, and you need to understand how you're going to exploit that mine. Exploit's not the best word, but how you're going to use the subsurface for that. So and I think maybe one of the people who's going to come and talk to you, I think tomorrow from BGS, she will probably talk to you a little bit about this. But so we've run what you might call what we call here a health check. It's a sort of a health check on the state of the environment which we went further than the traditional mineral exploration people. You may have seen some of this where they fly geophysical planes around and they look at the geophysics and they use that to find mineral deposits. It's gone further than that. Whereas we've flown a plane around and we've done airborne magnetics, radiometrics, but we've also analyzed the soils and the sediments in the streams. We've also done what's called airborne LiDAR. So we have, LiDAR is essentially sort of radar photography. So we have an incredibly high resolution LiDAR image of this area, which actually goes down below 1 meter resolution. So we can actually look at really high resolution topography in the area. We also did an ecological assessment with one of our sister institutions called the Centre for Ecology and Hydrology. And interestingly, the LiDAR was flown by the British Antarctic Survey. So you had the British Antarctic Survey using their planes, which were not down in the Antarctic for the Antarctic summer. We're up in the UK flying some of this area doing the LiDAR, BGS doing the geology, and the Centre for Ecology and Hydrology doing the ecosystem assessment. And so you're providing yourself with a baseline against which you can measure the environmental impact of what's going to go on. And so you're providing the community who live there with some sort of reassurance that you know what the situation is now, what the baseline looks like, and you know that if you're going to pollute that baseline, you can identify it. That's one of the big problems in the past, actually, is that, an example being shale gas in the US, where they went at it much too fast. They didn't do baseline, so you don't actually know what the situation was. So they've been accused of polluting groundwater with methane, but in actual fact, you don't actually know what the methane level was before they even did the fracking. Now, I think they probably did in some cases pollute it, but you need to have that baseline. So that's the sort of thing that sort of fits to this sort of what I call lighting up the subsurface. Here is actually lighting up the surface, but it's putting a really high resolution image at the surface, but then being able to project that to depth. So just so you know what this is, by the way, this is Cornwall. It's the sort of the southwest bit of England, all right? And this is it's actually a low resolution image here, but it's actually very high resolution. I can zoom in to about 1 meter resolution on this thing. And this is essentially, I don't know what actually, potassium, uranium, and thorium plotted in a diagram. So these different colors represent different sort of chemical characteristics of the subsurface. And these blobs, these blue-purple blobs here, right, are the famous Cornish granites that you might have heard about, right? So these are granites. So Dartmoor, you've heard of Dartmoor? Probably somebody might have heard of Dartmoor. Anyway, so Dartmoor is one of these granites that's fairly well known, and a lot of the tungsten and the copper and such like was mined in Cornwall and Devon, was mined around the edges of these plutons. So by doing this sort of work, actually, we can. In the old days of the geological survey, you would map these plutons here as a blob on a map, and you'd have a sediment and a granite. Now, with the sort of work we've done, we can actually start to define a depth, or the shape of the pluton at fairly shallow depth, much better than we knew before. Now, that has important implications, one, for localized, because then you start to understand how the fluids that circulate in the crust are sort of localized along the edges of the plutons, and how they move in and out of cracks and fractures in those plutons. When I say pluton, I mean a big lump of rock. Sorry for those who don't know that word, right? And so focusing the fluids around the edge of that results in the mineral deposition. So the tungsten deposits, the tin from Cornwall, is all formed around the edges of these granites. But also, interestingly, if you want the main theme of the conference, these granites are also the hottest, because they're quite rich in potassium. They also have the highest geothermal gradient in the UK in that area. So it's essentially the hottest part of the United Kingdom if you drill down at depth. And there has been in the past geothermal exploration in the area, and there will be actually in the future geothermal exploration, and probably there's a significant amount of European money going in at the moment to develop geothermal activity around these areas. So if you're developing geothermal activity, you need to understand the subsurface properly and well, and be able to reassure the the people who live there. So these are some of the lower carbon solutions that I talked about. All right? And I put lower in brackets, ER, because some people may or may not. So some of them are low carbon, and some of them are potentially not lower carbon, and there's an argument about that. So radioactive waste storage, right? So we have to store our radioactive waste underground. At least that's the accepted norm for most countries nowadays. And in Europe, the only country that's actively starting to store its radioactive waste underground is Finland. So they have a deposit which is now a repository which is now being developed. Sweden are moving quite fast. The French are moving quite fast. The UK is moving quite slowly. The UK is moving quite slowly because we've been very poor at communicating the process with the public. Essentially, they've been stopped about 15, 20 years ago because the communication process was poor. Essentially, the plan was to put the nuclear waste underground, but on Ministry of Defense sites. So there was very little communication as to where it was going, and so the public said, stop. Please stop. And now they're starting again. And so I'm going to come back to that, this sort of public communication type things. And that really is an important part of your teaching nowadays, I imagine. This is the whole social acceptance of geoscience as a whole, as a subject. So this is actually quite a good low carbon solution because it's what's called compressed air storage. And I'm not sure how many people realize, but I think you must realize that when we produce energy through windmills and tidal systems and renewable systems, sometimes we produce too much energy and we want to be able to store it. And so there's a lot of people starting to think about about storage of energy in general, not just geologicals, batteries and various things as well. But there is one relatively simple way of storing energy is through compressed air. And it's been done before, but it's now the technology is being honed and improved and such like. And essentially, it's simply capturing the excess energy and pressurizing air in underground caverns. That kind of it sounds simple, but essentially it is quite simple, but clearly there's geological complications around it. And what you do is you do it in the easiest underground cavern to use is a salt deposit. So salt deposits, you can drill a hole in it, you can spray hot water in it, so you can mine out a cavern inside the salt, all right? Put a cap on it, and then put compressed air in it. And the compressed air, because you're using compressed air, you compress, decompress, compress, decompress, compress, decompress all the time, all right? So it's quite an interesting question, actually, as to how well do we understand how the rocks will behave, or the salt, when you're compressing it, when you're doing this to it all the time, compressing it, decompressing it. So you can do you need to monitor that to understand it. But compressed air storage is a viable energy system that will develop more and more as a means of holding energy during the peak periods, so that you can use it again later. Shale gas, I'm not going to talk, I will talk a little bit about shale gas. I think you've had talks on this in the past, probably not the same teachers, are you? That's true, you don't come every year. And I could talk to you for a lot about shale gas, but I won't. But the UK is going ahead with the development of its shale gas. Is it a lower carbon solution? It's arguable. In actual fact, if you burn shale, it produces about half the amount of carbon dioxide as the coal does. All right. So if you replace globally coal with gas, you probably remove 2 wedges in that initial sort of wedge diagram that I showed you. Right? Now that's global replacement, which is probably almost impossible. But so you could argue that it is or it isn't a low carbon solution, but some countries are going ahead with it, and we need to be able to reassure the population that we understand how it happens, et cetera, et cetera. So we need to do research around the processes of shale gas. So that's something I'll come back to in a second. Carbon capture and storage you're aware of, right? So carbon capture and storage has become an expensive technology. Carbon capture and storage coupled with coal-fired power stations or with gas-fired power stations or on cement factories is a very good solution, or is potentially a good solution for getting rid of the carbon dioxide that you produce in those processes. It requires you to inject the carbon dioxide underground and sequester it underground. So you have to understand the subsurface to do that. Its main problem at the moment is that the price of carbon dioxide is too low, and the cost of the process is too high. So the cost of the process is probably about running at the moment about $50 a ton, and you need to get it down to sort of $20 a ton. Now that may well happen. I mean, there are developments happening at the moment in carbon capture and storage which will push the price down. Plus, I think as the economy recovers, the price of carbon dioxide will be pushed up. So there may be a point at which it becomes feasible. And interestingly, some of the oil and gas companies, now you may be skeptical. Shale, for example, is saying our future is in carbon capture and storage. Now you could argue that they're saying that simply because they want to sell more oil and gas. But but they are saying that. Geothermal, you know about that, but that's clearly, again, understanding the subsurface. So I'm meeting some people later on today where there's a proposal from the International Continental Drilling Program to drill into an active magma chamber on Iceland. So to actually drill a hole into the magma chamber, or as close as you can get to the magma chamber, so that you essentially produce energy forever, right? Are there any Icelandic people here? Yeah? No? It's an interesting one as well. You need to understand the subsurface. There's a lot of geothermal already in Iceland, but geothermal in Iceland is mainly on heated water systems. But this is getting into what's called the supercritical zone when you get next to the magma chamber, so you're constantly heating things up. It's an interesting concept. They tried it about 10 years ago, and they actually drilled across what was probably a sill of molten magma, and the magma came out of the drill hole on the surface. So I guess you got to get it right, and that shows why you have to get it right. But I think, yeah, it's viable, and there's an argument that Iceland can get some of its energy to Europe using underground cables relatively inexpensively if that develops. Or what they're doing already in Iceland is the energy they have in Iceland is used. Companies are locating their aluminium smelting plants and such like in Iceland, so high energy type industry is locating itself there. Again, the Icelanders want to be sure that we understand what we do and we're not polluting the groundwater, et cetera, et cetera. So even though we're researchers, we are kind of seen by some of them as part of the problem. So trying to, I think some of you are probably looking at me and saying, he's already sort of crossed the floor to the dark side. He already believes in, sort of polluting the planet and everything else because I'm a geologist and I'm doing that sort of stuff. Well, no, but I don't think we have an alternative but to use the subsurface, and we'll have to do it more and more as time goes on. And we have to do it in highly populated areas too. So in the UK, we've had a lot of problems. This is mainly, it's actually not, these are some examples of various sort of public reactions, this thing. This is nuclear, no to nuclear. Here, this is a CO2 injection plant in Germany, actually, I think, in Germany, Holland maybe, I'm not sure. Is that German? Is that Holland? Is that German? It's written there? Could be Dutch in that case. Anyway, it's a carbon dioxide sequestration plant. Some people are concerned that actually sequestering this carbon dioxide is dangerous because when it comes out again, or if it comes out again. This comes from a film. I think that's German, right? That's Dutch. That's Dutch, is it? Okay, sorry. Excuse me. I speak French, but that's about it. So, sort of these sorts of scenarios which are completely stupid, that, the carbon capture and storage blowout might use it. So how do we reassure the population about these sorts of things? And this is fracking in southern England. Get the frack out of Sussex. And actually, the drilling that was happening in southern England was not fracking at all. It was conventional oil and gas drilling, but it actually telling the population that and trying to get them to understand, they don't see the difference between conventional drilling and fracking and such like. So, how do you deal with this? And as I said, there is a resource. This is the UK. This is northern UK. This is so Liverpool is around here. Manchester's over here, if you know that. Those the blue lines all over on this map here are seismic lines. So that's geophysics, which was shot in the 60s and 70s. So in actual fact, we've known for a long time that there is oil and gas in the UK, all over the UK actually. It's a fairly rich oil and gas province. But we moved, the entire oil and gas operations moved offshore when North Sea oil really took off. So that essentially shifted offshore. It shifted to what you might call out of sight and out of mind, because it's offshore. People don't quite know what's going on, and although it is monitored, it's certainly not like having an oil rig in a farmer's field in the middle of Cumbria or something like that, right? So how do you deal with it? And the black, the drill holes where the BGS has a record, we have a core store, we have all this sort of information. And for those geologists in here, well, I'll try and keep it simple, the spine of England is a sort of carboniferous spine, what's called a carboniferous, about 350, 400 million years old, rocks that are part of what's called an anticline. So basically, the rocks go up under here, up here, and under here, all right? So these yellow formations here are what's called the Boland Shale, and it's an organic rich shale, which when you go down in depth, so when you get to about 3 kilometers under here, there are thousands of feet of organic rich shale underneath England, right? Thousands of feet. In contrast to the United States, where some of the shale gas operations are actually about 50 meters thick. They're thin, but they extend across an entire state. In the UK and elsewhere, actually, in Europe, but in the UK in particular, because of our geological location, they're very deep basins. So you've got a mile thick, or 2 kilometers thick, of organic rich shales down there. So that's why the companies are interested, and that's why, so we were asked, the BGS was asked to do an estimate of what we thought was there so that we could sort of reassure the population, actually reassure the government, that maybe there was something worth going for. So our estimate is actually that there's 1,300 trillion cubic feet. That probably doesn't mean anything to you really in terms of things. And that's a resource estimate. So that's, if you take the entire volume of rocks and you assume they've got 3 or 4% carbon and you extract it all, that's what you would get, right? That's the resource. And I think you may be hearing a bit about resource related to reserve this week. The reserve is what you can actually extract. And the same thing goes for minerals. The resource can be big, the reserve is what you can actually get out of the ground. So the reserve estimate, if you extract, and that's what the question is, what you need to test it. If you extract about, say, 5 to 10% of that, you probably have, I'm not supposed to say this in public, but you probably have 2 North Sea oil worth of gas, right, in just there. So there is potentially a large resource. Now that's a sort of finger in the air type thing. So what you need to do is to really develop it and to work and to see what is there. And so the companies are all, so I'll just go through that quickly. There are companies looking all over the UK for this. As I said, there are also mineral prospects in the UK. So the UK is a highly populated country, as is Europe as a continent. So the problem is, how do you deal with that in this sort of populated area? So here you've got the UK. I'm not sure about this. For some reason, there's no one Welsh here, because Wales has disappeared. I'm not quite sure why, but anyway, Wales is sticking on the side of here. But this is essentially population of the UK, and the areas of high population, apart from the south, but sort of in the north and in here, and in Europe around sort of Holland, these parts of Germany and such like, are areas that were essentially industrial in the past, in general. And the reason they were industrial in the past is because they had coal, because they had limestone, and because they had ironstone. Essentially, the 3 things that you need for a chemical industry, for industry, right? They had those 3 things. The Carboniferous of the planet gives us all three things quite nicely, and you can use those to underpin energy industries and chemical industries in the Industrial Revolution. So that's why there's a high population there. So in the UK, there's a lot of people live here. So how do you deal with that? How do you deal with the population relative to this sort of subsurface conundrum that we're talking about? So we need our people to be confident about our ability to do this. I'll just go through this quickly. This is just old people. So what we're proposing, and we think this sort of concept will develop, and as I said, we've got some quite serious amount of money for it, is that we're developing a unique package of monitoring and research capability at the subsurface, in what's called the critical zone, which is the zone sort of between where you live or where agriculture starts and the subsurface, and also in deep boreholes. And we wanted to monitor a bunch of variables, such as pressure, temperature, heat flow, seismicity, tilting, strain accumulation, all these things, mineral chemistry, pH, biology, and such like. Now, we want to be able to for you as teachers or people sitting at their home in their kitchens, to be able to click on a computer and see what's going on in their backyard, right? So that they feel comfortable about what's going on. Now, I don't think many people will bother, but if they do feel that they can, then it allows a certain confidence. As teachers, very soon, and I can probably via Carlo send you the link to this. We haven't got it live yet. You should be able to use our live monitoring for your teaching very soon. We'll have boreholes and such like being monitored, and you can look at them. I'll just show you. And so it kind of looks like this, right? So this is the view of it, and this is a sort of a generalized view. So you've got, as I said, these sorts of things going on. You've got carbon capture and storage, where your power plants capturing the energy and then capturing the CO2 and then storing it underground in reservoirs. You've got oil and gas, which actually oil and gas in general is, certainly in the North Sea, is decreasing. And how much time have I got left? 5 or so, all right. And airborne surveys, I showed you about these, et cetera, nuclear waste storage, and fracking. Don't forget fracking as well. Shale gas fracking is deep, right? So most of the shale gas formations are, well, they have to be actually at around 2 to 3 kilometers down, because they have to be pressurized in the right sort of oil and gas window. Often you see sort of diagrams in the Guardian newspaper in the UK in particular, where it kind of looks like the fracking is going to happen sort of just underneath in the groundwater zone, right? So here you've got the groundwater zone, which is sort of hundreds of meters, and here you've got 2 kilometers down. So the fracking will happen down here, right? It has to, by definition, to be able to pressurize things. So anyway, that's the situation. So the argument is, the arguments are that we need to actually develop something like this, which allows the public reassurance, but not only public reassurance. Being British, we like to make money. Apparently, we're a bit like the Dutch. So essentially, as well as allowing this reassurance, we also want to to help the industry improve itself, so that the industry so we can create what's called, if you want, a sustainable, a responsible geoenergy industry in Europe. And let me give you a relatively simple example, and the government is very much behind this. For those of you who are aware of fracking and such like, in the US, a fracking truck is say that big, right? They're great, big, noisy, smelly, dirty things, right? That's because in the US they don't care, with all due respect. No, but because it's a big country. I mean, you've seen trucks just a regular truck in the US has a big front end to it, right? So they're just big and noisy, and they're not necessarily high tech. Now, there are people I know at a university up in Scotland actually who are working on. So a fracking truck has got a big motor, a noisy diesel motor. Actually, you can replace that with a Formula 2 engine for about the same price, for about that size, right? And then they've got a sort of a gearing system which is old and clunky. You can replace that with a nice simple gearing system. Then you've got the front end of the truck, which is big and noisy, and you can replace that with something fairly quiet and maybe even electrical. So you can actually take a fracking truck like that and reduce it to something which is maybe that big at a relative scale and is quieter and more effective, right? More efficient. And that, I mean, it's the difference between, say, a Mercedes truck and a Ford. It's sort of because we're in the UK, in Europe, we have to deal with sort of a population that is a lot more environmentally aware. And I think the US is moving that way. So that simple argument with a fracking truck, you can multiply that over a whole bunch of things to actually make the entire industry acceptable in very big inverted commas, right? So anyway, what we think this underground laboratory system that we're going to develop is, first of all, it's an opportunity to reconnect applied earth science research with discovery science, with the more discovery side of research. There in earth sciences or in the geology, there's a disconnect between applied research and fundamental research. You tend to either do one or the other. Tend to, not exactly true, because I know some people, Steve does a bit of both, but in general, you either get funded by the oil and gas and mineral industry and do your thing, or you get funded by a research council to do researchy things, and there's not enough connection between the two. So we think this is a connection to try and improve that. So for example, I mean in this laboratory we're setting up, we're going to probably multiply by at least 5 the number of seismometers, actually more like 10 on that space. So those seismometers, very high density seismometers, as well as allowing you to look at the subsurface, will allow you to look at the deep subsurface, to look at the core mantle boundary better than we've ever done before. So there's other science you can do. Understanding the biosphere at 1 or 2 kilometers down properly, and actually doing experiments down there in situ is something you should be able to do. So again, an opportunity to reconnect our sciences and, as I said, act as a catalyst for industry. So actually to try and catalyze industry and grow industry. And the big thing, the big shift that's happening is, you're going to kick me off. the big shift that's happening across the world, actually across Europe, let's put it that way, and in particular in the UK, is that the oil industry, mineral and oil industry, is willing to open their databases. The oil industry was known and mineral industry was very poor releasing the databases. Now they are willing to open it. And I'm going to go there. This is the first site that we're going to set up, all right? And it's there. It happens to be, so I would say within 6 months, if not earlier, this site we will start having baseline instrumentation and such like. So this is here, for those of you who know Britain, that's Liverpool. This actually turns out to be the Shell research site. So Shell had a research laboratory there at Thornton that they abandoned 2 years ago. And being an oil company, they just delocalized everything, or the people, and they left their benches with mass spectrometers that are still turned on and working. Amazing. But it turns out that this Shell Thornton site also sits on top of 6,000 feet of shale gas. So we will do at this site, we will do the first research frack ever done on the planet. So we'll with the companies, we'll drill down, we'll instrument before, afterwards, and during, and we'll do a real research frack to try and really understand the process, right? At the same time, that can be used for other things, for example, biology and such like. At the same time, we'll also deploy arrays of drill holes for groundwater, to look for groundwater contamination, to monitor the groundwater, and seismicity, et cetera, et cetera. So that's a big change in the way we deal with these things, and I think I'm coming to the end. And as I said, you should be able the aim, in fact, the ambition, not the ambition that we will allow you to monitor this real time from anywhere. And we're modeling this a little bit after the Canadians working in the Alberta oil sands. Because clearly oil sands are probably, I would say, actually worse than fracking, potentially. But the Alberta government is putting in place a monitoring system so that people can see what's going on. So your students, if they're interested, or you, should be able to soon dial in and see what's going on in any borehole, any seismicity and such like, and to really start to understand the subsurface. So that the aim is that, as I said, on the scale of your lifetime, right, you will be able to, or you should feel confident that we understand what's going on below your feet. And that really is what we're trying to do. Because I think unless you can do that, a lot of these low energy solutions, or a lot of these mining solutions in Europe will never happen. And there will be a move, in general, there is a move afoot, you can see it actually, to more indigenous energy and mineral supplies. People want security of supply in their countries. not just for energy, but also for minerals. So that's why you see things coming back towards Europe, for example. And the US, actually, the US will have security supply, will be entirely self-sufficient in oil and gas by 2020, I think. And you can see the effects that is happening on gas prices at the moment, and actually on the whole geopolitics. I mean, with all due respect, the US seem to be quite a lot less interested in the Middle East than they ever were in the past. And I think it's largely because they've got their own energy supplies now. And you will see South America coming out. Places, Uruguay, Argentina, and places like this do have relatively large geoenergy resources. So they'll start to exploit those. But our hope is that this sort of system, let's go there, this sort of system that we want to develop will actually sort of evolve around the world. And they're already, the Australians are doing something similar, the US are doing a couple of things, we're doing this, there's something in Switzerland happening. The whole ability to sort of monitor real time and to really understand the subsurface is where we need to get to, and to do any sort of resource work in the future. Thank you very much.